When installing Greenfield, also known as flexible metal conduit or FMC, understanding the proper strapping methods is crucial for ensuring a safe and code-compliant electrical installation. Firstly, let's discuss the strapping pattern for vertical runs. According to standard practices, vertical runs of Greenfield FMC should be secured every 48 inches. This means that you need to use straps to attach the conduit to a supporting surface at intervals no greater than 48 inches along its vertical length. It is important that these straps are wrapped around both the conduit and the supporting surface. This ensures that the conduit is firmly held in place and prevents it from moving or sagging over time. Secondly, let's examine the strapping pattern for horizontal runs. For horizontal runs of Greenfield FMC, the strapping requirements are slightly different. In this case, the conduit should be secured every 36 inches. However, unlike vertical runs, the straps only need to be secured around the conduit itself and not to the supporting surface. This is because horizontal runs are generally less prone to sagging due to gravity, and the straps primarily serve to maintain the conduit's alignment and prevent it from shifting laterally. Now, let's address an important exception to these general strapping rules. Conduits with a trade size of 1/2 inch or less may be secured at intervals no greater than 6 feet. This exception is based on the fact that smaller diameter conduits are less likely to sag or bend compared to larger conduits. Their inherent rigidity allows for a greater spacing between supports without compromising the integrity of the installation. This exception can save time and materials, particularly in situations where numerous short runs of small diameter conduit are required. Next, let's move on to the topic of adjustment factors for conduits with multiple networks. When a conduit contains multiple current-carrying conductors, it is necessary to apply an adjustment factor to the ampacity of those conductors. This is because the heat generated by the conductors can accumulate within the conduit, potentially raising the temperature above the insulation's rating. To prevent overheating and ensure safe operation, the National Electrical Code, or NEC, requires that the ampacity of the conductors be reduced based on the number of current-carrying conductors in the conduit. In the specific case of a 3/4 inch conduit containing 3 networks, an adjustment factor of 0.8 is typically required. This means that the allowable ampacity of each conductor must be reduced by 20%. For example, if a conductor has an initial ampacity of 30 amps, applying the 0.8 adjustment factor would reduce its allowable ampacity to 24 amps. It is crucial to consult the appropriate NEC tables and sections to determine the correct adjustment factor for a given number of conductors and conduit size. The number of current-carrying conductors is a key determinant of the adjustment factor. As the number of conductors increases, the heat generated within the conduit also increases, necessitating a greater reduction in ampacity. The NEC provides tables that specify the adjustment factors based on the number of conductors. It is important to note that certain conductors may not need to be counted when determining the adjustment factor. For example, equipment grounding conductors and conductors that are only used for signaling or control purposes may not need to be included in the count. However, it is always best to err on the side of caution and consult the NEC for specific guidance. The fill ratio, or the percentage of the conduit's cross-sectional area occupied by conductors, also plays a role in determining the need for adjustment factors. The NEC specifies maximum fill ratios for different types of conduits. Exceeding these fill ratios can lead to overheating and damage to the conductors. Therefore, it is essential to calculate the fill ratio before installing conductors in a conduit to ensure that it complies with code requirements. Failing to apply the correct adjustment factors can have serious consequences, including overheating of conductors, insulation breakdown, and even electrical fires. Therefore, it is crucial for electricians and electrical contractors to be knowledgeable about these requirements and to follow them diligently. In summary, when installing Greenfield FMC, remember to secure vertical runs every 48 inches with straps around both the conduit and the supporting surface, and horizontal runs every 36 inches with straps around the conduit only. Be aware of the exception for conduits with a trade size of 1/2 inch or less, which can be secured at intervals up to 6 feet. And finally, always apply the appropriate adjustment factors when installing multiple networks in the conduit to ensure the safe and reliable operation of the electrical system. Now let's delve deeper into the specifics of conduit installation and the factors that influence strapping and adjustment requirements. The type of supporting surface to which the conduit is being attached can affect the choice of strapping method. For example, when attaching conduit to concrete or masonry walls, it may be necessary to use anchors or fasteners that are specifically designed for those materials. Similarly, when attaching conduit to metal studs or framing, it may be necessary to use self-drilling screws or other fasteners that are compatible with metal. The environment in which the conduit is being installed can also affect the choice of strapping and adjustment methods. For example, in corrosive environments, it may be necessary to use straps and conduits that are made of corrosion-resistant materials such as stainless steel or PVC-coated steel. Similarly, in high-temperature environments, it may be necessary to use conductors with high-temperature insulation ratings and to apply additional adjustment factors to account for the increased heat. The presence of other equipment or structures in the vicinity of the conduit can also affect the installation requirement. For example, if the conduit is located near a source of vibration, it may be necessary to use straps that are designed to dampen vibration and prevent the conduit from loosening over time. Similarly, if the conduit is located in a confined space, it may be necessary to use flexible conduit or other methods to route the conductors around obstacles. The National Electrical Code, or NEC, is the primary source of information on conduit installation requirements. The NEC is a comprehensive set of standards that covers all aspects of electrical installations, including conduit sizing, strapping, and conductor ampacity. It is essential for electricians and electrical contractors to be familiar with the NEC and to follow its requirements diligently. The NEC is updated every 3 years, so it is important to stay current with the latest edition. In addition to the NEC, there may be local codes and regulations that govern conduit installations. These local codes may be more stringent than the NEC in some cases, so it is important to be aware of them and to comply with them. Local codes are typically enforced by local building departments or electrical inspectors. Electrical inspectors are responsible for ensuring that electrical installations comply with the NEC and local codes. They typically conduct inspections at various stages of the installation process, including before, during, and after the installation is complete. It is important to cooperate with electrical inspectors and to address any concerns they may have promptly. Proper conduit installation is essential for ensuring the safety and reliability of electrical systems. By following the NEC and local codes, and by using proper strapping and adjustment methods, electricians and electrical contractors can help to prevent electrical hazards and ensure that electrical systems operate safely and efficiently. The long-term performance of an electrical system is directly related to the quality of the installation. A poorly installed conduit system can lead to a variety of problems, including conductor damage, insulation breakdown, and even electrical fires. Therefore, it is essential to take the time to do the job right and to use high-quality materials and workmanship. Continuing education is an important part of being a skilled electrician or electrical contractor. The electrical industry is constantly evolving, with new technologies and techniques being developed all the time. By attending continuing education courses and seminars, electricians and electrical contractors can stay up to date on the latest trends and best practices. This can help them to improve their skills, enhance their knowledge, and provide better service to their customers. Furthermore, different types of Greenfield FMC exist, and their specific installation requirements might vary slightly. For example, liquid-type flexible metal conduit, or LFMC, requires specialized fittings and sealing methods to maintain its liquid-tight integrity. When working with LFMC, it's crucial to follow the manufacturer's instructions and the NEC guidelines for proper installation. These guidelines will cover the appropriate types of fittings, sealing compounds, and strapping methods to use. Ignoring these specific requirements can compromise the conduit's liquid-tight seal, potentially leading to water damage and electrical hazards. Similarly, other specialized types of flexible metal conduit, such as shielded FMC used for sensitive electronic equipment, may have unique installation considerations. Always refer to the product documentation and relevant codes to ensure that you're using the correct methods for the specific type of conduit you're installing. The proper selection of straps is another critical aspect of Greenfield FMC installation. Straps are available in a variety of materials, sizes, and designs, each suited for different applications. Metal straps are commonly used for general-purpose installations, while plastic straps may be preferred in corrosive environments. The size of the strap should be appropriate for the diameter of the conduit, ensuring a secure and snug fit. Additionally, the design of the strap can influence its effectiveness in supporting the conduit. Some straps feature a single screw or bolt for attachment, while others have multiple fasteners for added stability. When selecting straps, consider the weight of the conduit and its contents, the environmental conditions, and the specific requirements of the installation. Using the wrong type or size of strap can lead to conduit sagging, loosening, or even complete failure. In addition to strapping and adjustment factors, proper grounding and bonding are essential for a safe and effective Greenfield FMC installation. Grounding provides a path for fault current to return to the source, tripping a circuit breaker or fuse and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of voltage differences and shock hazards. When installing Greenfield FMC, it's crucial to ensure that the conduit itself is properly grounded and bonded. This can be achieved by using appropriate grounding bushings, lock nuts, and bonding jumpers. The specific grounding and bonding requirements will vary depending on the type of system, the size of the conduit, and the applicable codes. Always consult the NEC and local codes for detailed guidance on grounding and bonding Greenfield FMC. Improper grounding and bonding can create dangerous electrical hazards, so it's essential to pay close attention to these details. Also consider the impact of future modifications or additions to the electrical system. When planning a Greenfield FMC installation, it's wise to anticipate potential future needs and to design the system with flexibility in mind. This might involve using larger conduit sizes than initially required, providing extra pull boxes or junction boxes, or installing spare conduits for future expansion. By considering future modifications, you can avoid costly and disruptive rework later on. Furthermore, accurate documentation of the Greenfield FMC installation is crucial for future maintenance and troubleshooting. Keep detailed records of conduit routing, conductor sizes, and adjustment factors. This information can be invaluable when making repairs, adding new circuits, or performing inspections. In addition to written records, consider taking photographs of the installation before it's concealed by walls or ceilings. These photographs can provide a visual reference that can be helpful in identifying conduit locations and routing. In addition to the adjustment factor mentioned earlier, other factors can affect the ampacity of conductors in a conduit. For example, the ambient temperature surrounding the conduit can impact the conductor's ability to dissipate heat. If the ambient temperature is high, the conductor's ampacity must be reduced to prevent overheating. The NEC provides tables that specify ampacity correction factors for different ambient temperatures. Furthermore, the type of insulation used on the conductors can also affect their ampacity. Conductors with high temperature insulation ratings can carry more current than conductors with lower temperature ratings. When selecting conductors for a Greenfield FMC installation, it's important to choose conductors with the appropriate insulation rating for the application and the ambient temperature. It's also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The amount of voltage drop in a circuit depends on the length of the conductors, the current flowing through the conductors, and the size of the conductors. The NEC provides guidelines for calculating voltage drop and for selecting conductor sizes that minimize voltage drop. When installing Greenfield FMC, It's important to follow these guidelines to ensure that the voltage drop in the circuit is within acceptable limits. Furthermore, consider the potential for electromagnetic interference, or EMI, in the Greenfield FMC installation. EMI can occur when electrical signals from one circuit interfere with signals in another circuit. This can cause problems with sensitive electronic equipment such as computers and communication devices. To minimize EMI, it's important to separate power circuits from signal circuits and to use shielded conduit and conductors. Shielded conduit and conductors have a metal layer that blocks electromagnetic radiation. When installing Greenfield FMC in areas where EMI is a concern, it's important to use these shielded products to protect sensitive electronic equipment. Finally, remember to always prioritize safety when working with electricity. Electricity can be dangerous, and it's important to take precautions to protect yourself from electrical shock and other hazards. Always wear appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. Before working on any electrical circuit, always de-energize the circuit and verify that it's de-energized using a voltage tester. Never work on live electrical circuits unless you're properly trained and authorized to do so. By following these safety precautions, you can minimize the risk of electrical accidents and injuries. When dealing with multiple networks within a single conduit, you also need to carefully consider the type of equipment each network serves. If the networks serve critical equipment or systems such as emergency lighting, fire alarms, or life support systems, you might need to provide additional protection or redundancy. This could involve using separate conduits for each network, installing backup power supplies, or implementing other measures to ensure that these critical systems continue to operate in the event of a failure. The NEC provides specific requirements for critical systems, and it's important to follow these requirements carefully to ensure the safety and reliability of these systems. Also keep in mind the potential for future expansion or changes to the electrical system. As technology evolves and building needs change, it's likely that the electrical system will need to be modified or expanded. When installing Greenfield FMC, it's wise to anticipate these future needs and to design the system with flexibility in mind. This might involve using larger conduit sizes than initially required, providing extra pull boxes or junction boxes, or installing spare conduits for future expansion. By considering future modifications, you can avoid costly and disruptive rework later on. Also make sure to properly label all conduits, pull boxes, and junction boxes to clearly identify the circuits and networks they serve. This labeling should be durable and easy to read, and it should comply with the NEC requirements. Proper labeling makes it easier to identify and troubleshoot circuits, and it can prevent accidental disconnections or misconnections. It's also a good practice to create a detailed wiring diagram of the Greenfield FMC installation. This diagram should show the location of all conduits, pull boxes, junction boxes, and equipment, as well as the size and type of conductors used. The wiring diagram should be kept in a safe and accessible location, and it should be updated whenever changes are made to the electrical system. A well-maintained wiring diagram can be invaluable for troubleshooting, maintenance, and future modifications. In addition to the technical aspects of Greenfield FMC installation, it's also important to consider the aesthetic appearance of the installation. Conduit should be neatly and professionally installed, with straight runs and consistent spacing. Straps should be properly aligned and securely fastened. All fittings and connectors should be clean and free of debris. A well-executed Greenfield FMC installation not only functions properly but also enhances the overall appearance of the building. When working on a Greenfield FMC installation, always be mindful of the other trades working in the area. Coordinate your work with plumbers, HVAC technicians, and other contractors to avoid conflicts and to ensure that the installation is properly integrated with other building systems. This coordination can prevent delays, reduce costs, and improve the overall quality of the project. Before starting any Greenfield FMC installation, it's always a good idea to conduct a thorough site survey. This survey should identify any potential obstacles, hazards, or challenges that might affect the installation. The site survey should also verify the accuracy of the drawings and specifications. By conducting a thorough site survey, you can avoid surprises and ensure that the installation goes smoothly. Finally, always remember that safety is the top priority. Work safely, follow the NEC and local codes, and use high-quality materials and workmanship. A well-executed Greenfield FMC installation will provide years of reliable service and will contribute to the overall safety and efficiency of the electrical system. Remember that local amendments or interpretations of the NEC may exist, so always check with the local authority having jurisdiction or OJ to ensure compliance with all applicable regulations. In some cases, the AHJ may have specific requirements for Greenfield FMC installations that go beyond the NEC minimum standards. The AHJ is the final authority on electrical installations, and their decisions must be respected. Therefore, it's always best to consult with the AHJ before starting any Greenfield FMC installation to ensure that the installation will be approved.